Hello and welcome to PyData Global 2021. My name is Natalie and I'm very happy to be here and be your host for this session. I would now like to welcome Alejandro Saucedo to our session, and he will talk about accelerating ML interface in inference at scale with ONNX, Triton, and Tempo. Alejandro is the Director of Machine Learning Engineering at Seldon Technologies. He is also the Chief Scientist at the Institute for Ethical AI and Machine Learning. And with that, I'll give the floor to Alejandro. Thank you for joining us today.
Thank you very much, Natalie. So I think with that, I'll kick off the session. Thank you everybody for joining. My name is Alejandro Saucedo, and today I'm going to be delving into accelerating machine learning inference at scale with ONNX, Triton, and Seldon, together with a couple of other tooling. So we have quite a lot of content to cover, but as mentioned, please feel free to put all your questions as I go along, and I'll be able to answer some as I go and others at the very end in the last couple of minutes. So let's get started. A bit about myself. I think my background was covered quite well. So just to provide a brief, I'm Engineering Director at Seldon Technologies, Chief Scientist at the Institute for Ethical AI, and Governing Council Member at Large at the ACM. A little bit about Seldon. So we are a machine learning deployment and monitoring open core company. So we actually built one of the most popular machine learning deployment tools for Kubernetes, which has been downloaded, a significant number of times and is used across various large-scale production environments. We have an enterprise product that basically builds on top of that to add monitoring and management. And at the Institute is basically a research center based in the UK that focuses on the development of frameworks for the responsible design and operation of machine learning systems. So with that, what we're going to be doing today is covering this challenge of machine learning acceleration at scale from a very practical perspective. So we're going to be taking a use case of a machine learning model that is a little bit more complex than the usual hello world type models like the Iris model or even CFAR10 or MNIST. In this case, it's going to be the GPT-2 TensorFlow model. We're going to optimize this model using ONNX and cover a bit more of what that exactly means. We're going to then be able to run this model locally to test it as a service, leveraging this tool called Tempo. And then we're going to be able to productionize it without much complexity into a scalable infrastructure, which in this case is going to be Kubernetes, but with the core premise that, as a data scientist, what the main principle on the focus would be is on the data science side, right? So this would require abstracting as much as it's feasible on the underlying infrastructure complexities, right? So the Kubernetes abstractions not needing to leak into the data science practitioners. So that is one of the key things as a premise. Now, to start with the what is GPT-2? So maybe several of the people looking at this talk may already be familiar, but GPT-2 is a generative model that allows you to basically generate text in a human-like way. You're able to provide a input, in this case, sentence, of course, in a preprocessed format, but what you would get is the next predicted token, which you would then be able to resubmit to the model and get the next token and the next token until you can create basically a human-like sentence. Now, why would we use this? And the reason is primarily for two main reasons. The first one is that this model is a relatively complex model, right? As I mentioned, it's not an iris classifier. It actually requires some compute, a reasonable amount of compute to both train and perform inference. And also the latter is, given that it is possible to actually create some very creative applications, right? And there has been quite a lot of very interesting use cases that have leveraged GPT-2 in basically what could be things like games, even as well as in some cases even code generation tools, which is on the more interesting side. But those are some of the more advanced models. But you can see here and get an intuition of how the applicability of this model could actually be relevant in many, at least interesting or fun applications. So hopefully by the end of this session, you will also have not just the intuition of how to accelerate and productionize a model, but also be able to get the foundation for you to get started and building something that could be quirky and cool. So how are we going to do this? The way that we're going to be able to do this is by first fetching a pre-trained model. We're not going to train it from scratch because the talk is only half an hour. This would take, unless I have tons of GPUs, not enough time. We're going to then be able to optimize the model and talk a little bit more about that. And we're going to be leveraging tools to productionize our model in a way that can be accelerated as well as tested both in a local environment and a remote scalable environment. So that's what we're going to be doing. As I mentioned, the code and examples and links are provided in these slides, and I shared those previously in the general chat, but you will see at the end the link to this presentation, which you will be able to access. Now, let's get started with the first step, which is going to be fetching the GPT-2 model. So we are going to be leveraging this library called Hugging Face. And the reason why is because Hugging Face has a very vast range of available pre-trained models that have been optimized and have been improved to an extent that we can actually just leverage them from this catalog or library of different things that are available. Specifically in our use case, we're going to be using the particular artifacts for GPT-2. And this consists of two specific components. And you can see it here, how we actually write explicitly from transformers, import GPT-2 tokenizer and TF GPT-2 head model. So you can see that on one side, we have a tokenizer, and in the other, we have a model. As we dive deeper, you will see how we use the tokenizer for pre-processing and the model for the actual inference. And then again, the tokenizer to actually convert it back to a human readable format. But it is as simple as just being able to fetch it. And we can now actually leverage these components locally. And what that basically looks like is as follows. If we actually take and start with a sentence, a human readable sentence that basically reads, I love artificial intelligence. What we would be able to do is before passing that sentence to the model, it requires some pre-processing. And what that is in specific detail is leveraging the tokenizer to tokenize each of the words in our input. So what we would have from I love artificial intelligence, we would get a set of machine readable tokens that we would then be able to actually send to the model. In this case, you can actually see that we're not using model.predict, but we're using model.generate. And if you remember, the way that the model works is it generates or it predicts a single token, right? In this case, by using the generate function, we are leveraging a utility that allows us to just not just run the model multiple times, but also select the next tokens in a particular way, which we will cover in a bit. In this case, we're saying we want to generate 20 tokens. And what we end up having is as the output, we have our original tokens and our next 20 tokens. These tokens are not human readable, so we're going to have to pass that back through the tokenizer using the decode as opposed to the encode, which would then give us this human readable output that reads, I love artificial intelligence, but I'm not sure if it's worth. So within 5 minutes, we have been able to get an intuition of what actually we would be able to do with this machine learning model. Now it comes to the question of, well, what is happening first of all in this generate function? So the underlying workflow that this generate function basically does is that it runs the inference multiple times for the model. However, one thing that we need to take into consideration is that every inference iteration that we execute with the model we actually don't get just one token. We actually get the list of all possible tokens with the probability of which of these tokens is the most probable to happen, right? And what we need to do is to actually choose the probability, the token with what would be our ideal selection. So in this specific case, there is actually a specific selection which is optimized in a way where it doesn't just take the next best performing token, but it actually has a look ahead, which is actually called a beam technique for selecting the next token. However, for simplicity in our use case, what we're going to be doing is we're going to just select the next token with the highest probability, right? So we're going to perform an inference. We're going to take the token with the highest probability. Then we're going to then run the inference again with this extra token and go on and on and on until we actually reach, in this case, the max length, right? So that's basically it. That's all you needed to know in regards to the intuition of what's happening with the model. Now, let's actually see how we're going to scale it. And more specifically, what are the challenges that we would face when looking at scaling the model, right? And what that actually would look like is, in regards to the challenges, as a practitioner, we know that there is a requirement for specialized GPU, right? Or specialized hardware more specifically, right? Some models may require large number of memory, large number of CPUs or GPUs, perhaps even like horizontal scaling with multiple GPUs performing like model parallelization or even data parallelization. There is not just specialized GPU, but also complex dependency between the components, right? We saw that we have a transformer and we also have a model, and there's a data flow between them. There is then challenges of reproducibility, right? The challenges of making sure that whatever we run once, we can actually identify what was the input and the output, and then be able to rerun it and get the same deterministic results. And then, of course, there is some higher level compliance requirements around what could be even more domain specific, industry specific, or use case specific nuances. So those are some of the high level things that need to be taken into consideration, which as a data scientist, we can all acknowledge that, not to say that, this wouldn't be their primary area of interest, because it may be of high interest, as I can see there's a large number of attendees to this talk. But as a practitioner, as a data scientist, their primary focus is the data science part of it, the machine learning, or to even an extended amount, the machine learning engineering part of it, as opposed to the underlying DevOps and infrastructure. And what tends to happen in a lot of situations with the context, in the context of MLOps tools, is that there is a lot of abstraction, particularly infrastructure abstraction, that leaks into the domain of data science. Right? And this is something that we want to avoid. And this is a principle that we want to approach, particularly one of the reasons that led us to develop this framework called Tempo and its underlying server, ML server. And we're going to talk about that. So the question is, how do we go from our model artifacts or custom code that we will need to actually put together, as you will see later on for the transformer code, into a fully fledged microservice that we can not only deploy, but also test locally and scale and optimize without having to deal with the underlying complexities of the infrastructure where it's being deployed. Now, that's what we're going to start doing. The first step is, let's optimize this model. Why would we want to optimize this model? Is particularly due to the challenge that I raised around specialized hardware and the potential workload that may require and may benefit from the actual best performance in the respective hardware where it's running. And a standardized format that is currently accepted, widely adopted in industry, is the ONNX format, which stands for Open Neural Network Exchange. And this is actually we can call it a schema or specification that allows us to transform, in this case, what could be our TensorFlow model or a PyTorch model into what is this standardized format. A standardized format that then other optimized servers, which we're going to be using, can read and then can also modify in whatever ways it needs to be able to ensure optimal performance, right? This is why we would want to do that. Having said that, you can follow all of the steps that we are doing without converting it into ONNX. You can still deploy your TensorFlow model directly. You can deploy your PyTorch model directly. In this case, we just wanted to show how you can also add this extra step of optimizing it. So now that we've optimized it, we want to productionize it. And in this case, we're going to be using this tool called Tempo and its underlying runtime called ML Server. And in this case, we're going to be using actually not just ML Server, but also the Triton Inference Server. And this will become a little bit more intuitive as we delve into it. The key thing that you want to get from this slide is that with Tempo, we're going to be able to first run it locally and then scale it up, right? And we would want to do this because you wouldn't want to actually push your artifact and then suddenly realize that it's failing and then have to ask for logs and then have to ask for a lot of things that would, again, go into the challenge of leakage of abstractions of the underlying infrastructure where it's actually running. So the way that we're going to be approaching this productionizing step with Tempo, what we're going to be doing is these 5 steps. The first step is we're going to actually define our Tempo wrapper for the GPT-2 model, right? And remember that the GPT-2 model is separate to the transformer. So that will be our first step. Once we define our wrapper, we can actually run that optimized model in this optimized server from NVIDIA, which would allow us to leverage this GPT-2 inference in a very sort of optimal performant way, right? So that's what we're going to be able to do that just on the first part with Tempo. But if you remember from the intuition that we gathered initially, our model doesn't take human readable strings, right? It actually takes machine readable tokens. So in order for us to actually interact with this service in an easy and simple way, and remember as well, because it only predicts a single token, we actually would like to have an extra component that allows us to basically send it the text, and then this component would handle all of the logic to talk to the model in those multiple times, right? To be able to request the next token and the next token and the next token, and then convert it back into a human readable format, right? So what that means is that we actually have to then define that custom transformer logic, which is going to be some Python logic that is going to perform that set of steps that we just described. And this will become a little bit more intuitive when you look at the code, right? Because right now it sounds very abstract. Once we see the code, it looks very, easy and simple to understand. Now, these 2 things, our wrapper and our custom logic, we can similarly just run it again in Docker, send some strings, get some predictions, but instead of just this specific one where we only get 1 token and we have to send the tokens, we can now just send strings, right? We can send strings to the transformer that would interact with the model and we would get the output. And we would be able to generate, 10 tokens and whatnot. And once we're happy that it ran correctly in Docker locally, we can then just very simply transition into our Kubernetes stack and then deploy that exact graph into Kubernetes with just a similar command that would basically just run that. So that's ultimately the only step that would have to happen from this one to this one. Now let's look at what that actually seems from a code perspective. So the first step, which is defining the wrapper, right? So what this looks like from Tempo, we have to actually import from Tempo the actual different types of model frameworks. We will see what that means. And we will then have to import the model class from Tempo. And in this model class, the only thing that we have to provide is the model name, the model runtime, which in this case is of type ONNX, because we actually optimized our model. But as I mentioned earlier, you can actually pass a TensorFlow model with model framework TensorFlow, or you can pass a PyTorch model with model framework PyTorch. So this basically allows you to define what is the actual artifact type. Then we can provide the path to where we have our model, the local path, and the remote path that will be relevant once we actually want to deploy it remotely, right? Because it needs to access the artifact. And then a description, right? Which is optional. So once we define our wrapper, we can actually run it locally, right? And this is just our model, right? So we're going to be just running the model locally with that Triton optimized server. So what we're going to be doing is we're going to call tempo.serve.deploy import deploy local. And then we're going to be able to run that object that we created through our deploy local function. That would then deploy it in Docker locally. and would give us this remote client that we're going to be able to interact with that model. What that really means in practice is that we can actually send tokens. And remember, we have to actually tokenize it. So we're going to have to go through those complex steps of taking our string, that is, this is a test. We're going to then have to convert that into the tokens, and then we're going to have to change this as the input to the model, and then call our model with remote model.predict. That would then give us a response, which again is in token format. This token format is, all of the potential tokens. We select the one with the highest probability. We then decode it, and then we can see what the next token is, which the next token is the word off, right? But this is very complex, right? As we said, we don't want to just have a model that all it receives is tokens. We actually just want to send this string. So that's where the next step comes in, which is building our custom transformer logic. And for this, we actually use not the model module or decorator, but we use the pipeline decorator. It has the same exact parameters, except this new parameter called models, where we actually are providing and passing that model that we defined above, right? So we're passing it this GPT-2 model. And now we can actually use it locally by providing the custom logic. The custom logic as a first step is going to consist of loading that artifact tokenizer, right? So we're going to put the logic to load that tokenizer. And then we have to define the predict function. And this predict function is going to be basically an abstraction on the REST endpoint that our service will expose. So whatever we actually are sending to the service through this simplified interface is going to be provided as this kind of, in this case, a input string, right? So in this case, we have to define the logic, assuming that we're going to be taking this as an input string. And what are we going to be doing here? You already probably have in the intuition. We are going to convert this string into tokens. We're going to then call this remote model for every single time that we want to, generate a next token. And then we're going to return, decode the tokens and return the output. What that really looks like, it may sound complicated, but it isn't really. We first define the number of tokens we want to generate. We then take that sentence that we received. Then we iterate for the number of tokens that we want basically to generate, which is in this case 10. We first convert or tokenize our initial input, which we receive here as all of the tokens. We do the same thing that we did locally, but inside of our custom logic, which is basically run an initial, a single inference execution, which will give us those outputs. We would then choose the one with the highest probability, decode it, and append it. And we're going to then do this, in this case, 10 times until we actually have a sentence with 10 extra words, which we will then return. And that's it. This is probably like the most complex part of this talk. And I hope that you managed to kind of like understand the intuition behind it. But the key thing is here is you pass a token, you run it through the model several times, and then you return it. Now, the key thing about this is that similar to our previous sort of example, we can run our pipeline in the same way locally by using the same function, deploy local GPT-2 transformer. We would get this remote class that we can now then interact. So we can now send a human readable string that in this case, it reads, I love artificial intelligence. And then the response is, but I'm not sure if it's worth whatever that means. What we have here is basically just a very simple way of interacting with this complex, data dependencies, with this data flow and this underlying infrastructure, which in our case is running locally in Docker. However, now we want the next step of let's then take what we are running locally in Docker and then run it in Kubernetes. This will actually be extremely simple. This is only a step of actually having to run it through the deploy remote as opposed to the deploy local. And I can see, Natalie, about to give the heads up on the 5 minutes, but yeah, we should be good. So no worries. Awesome. Thank you. Yeah. So now it's basically the question of how do we deploy it to the remote site? This is just using the deploy remote. So in this case, we would basically, just select some nuances of what is the namespace where we want to have it. And we would basically just leave the underlying infrastructure to be handled by Tempo to be deployed. And the interaction with that is the same thing. We can send a prediction of I love artificial intelligence, and we would get a response of, the same response, right? But I'm not sure if it's worth. Now, that's basically it. With that, you have now been able to go from, Jupyter Notebook to machine learning engineering local testing to MLOps productionization with a still not optimal, but at least minimized amount of leakage of the underlying infrastructure. So in summary, we were able to have a look at machine learning acceleration at scale by optimizing this GPT-2 TensorFlow model with ONNX, running this GPT-2 model in Triton with Docker, deploying this GPT-2 model in Kubernetes, and then assessing some of the best practices with all of these different components. Now, to wrap up, I just wanted to mention that this is one of our many different collaborations that we have been exploring with Tempo. We did a recent collaboration with the Metaflow team to be able to provide a full end-to-end training and deployment set of components, which you can find in this resource. All of these projects are open source, so any feedback is greatly appreciated. So, please do feel free to send any of these resources. And with that, I want to give a massive thanks to all the attendees and definitely the organizers, especially the chairs of this session. Thank you everybody for this. And now we can take some questions. Thank you.
There's one that is, what is the reason the library is called the Hugging Face?
Oh, that's a great question. I actually don't know. I think it's just because their name is their emoji, but this is actually a pretty renowned company and open source project that I encourage people to maybe find out, and given it's open source, maybe open an issue and ask, which is the beauty of open source. Yeah, I can see the chat. Happy to read it. So it says, it seems that it's much easier to deploy deep learning models for scalable low latency and parallel inference due to the extensive tooling support, rather than try to deploy something that lacks such support. That's a really good point. So interestingly enough, that is why I was mentioning several times the underlying runtime of Tempo, which is both Triton and ML Server. ML Server is actually the optimized framework for non-deep learning libraries like scikit-learn, XGBoost, LightGBM, etc. So you can actually still deploy this type of artifacts with the same level of reliability. Mm-hmm.
Okay, thank you. So our time is over. If you have any further discussion, please move it to Slack or GatherTown. Thank you so much, Alejandro, for your talk and being part of PyData Global 2021.
Thank you. Thank you, Natalie. And thank you, everybody. Great to be here.